Okay, guys, we're going to talk about acids and bases. This fits really nicely into our solutions chapter because acids and bases are typically going to be in solution form. And so let's just start with some basics. Let's talk about some properties of acids and bases. And so some properties of acids. Number one, acids are going to taste sour. They generally have a sour taste. And if you've ever bitten into a lemon, you would know that. Lemons have a fair amount of acid in them, and so they taste sour. Candies, like if you eat like real sour candy, sometimes they make candies that are sour on purpose. They put acids in those to make them taste that way. Bases, on the other hand, are going to taste bitter. And bitter is oftentimes a hard taste to describe because it's something that we generally tend to avoid a great deal. It's not like sometimes sour tastes good. Sour does taste good at times. Bitter just almost never tastes good. Examples, dark chocolate, unsweetened dark chocolate would be bitter. Coffee has a bitter taste to it to some degree, depending on how you make your coffee. And a real good example of bitter is like around Christmas time, you might be eating some pecans and you might get a piece of the shell in your mouth instead of the meat of the pecan, and that usually has a real bitter taste to it. Acids on the pH scale, we're going to be learning about pH here. Acids have a pH that is less than 7. Bases have a pH that is greater than 7. Acids are going to turn blue litmus paper red, and bases turn red litmus paper blue. So just little opposites. They're just indicators of whether or not an acid or a base is present. Another one for bases is that bases feel slippery. So if we ever are working with an acid-base lab and you and your fingers start to feel slippery or slimy, if you will, you probably got some of the base on you. Bases feel slippery. Soap is a good example. Soap is a base. Soaps are minor bases, and so when you wash with soap, your hands feel a little bit slippery. The last one is that both of these, an acid will react with a base will react with an acid. So they react with, this is kind of sloppy here, sorry about that, react with the other in a neutralization reaction. Looks like my 9-year-old wrote this. So anyway, those are some basic properties of acids and bases. Let's talk about the pH scale just for a second, then we'll get into some definitions of acids and bases. So the pH scale measures the strength of an acid or a base on a sliding scale, if you will. And we talked about real briefly about how the number in the middle, 7, would be neutral because acids are less than 7 and bases are greater than 7. So a pH of 7 is neutral. Anything less than 7 would be an acid. The further away from 7 it is, the stronger the acid is. And anything greater than 7 is a base. Again, likewise, the further away from 7 it is, the more basic it is. And so that's what our pH scale is. Our pH scale is based on an equation, which is a log equation. pH is equal to the negative logarithm of the concentration of the hydrogen ions in the solution. That is our pH scale. Do not, if you don't like math and you don't like logs, don't be scared of the fact that we're using logarithms here. We're not doing a lot of logarithm stuff. We're just going to be hitting the log button on our calculator to solve out these pH equations. And so that is your formula to solve for the pH of a solution. All you have to know is the concentration of hydrogen ions. So let us talk about this concentration and how it comes into play for a second. All right, so here's water. Water has a formula of H2O, and I have said sometimes it's useful to write water in the form of HOH. Instead of H2O. And water actually has that structural formula. It's an O in the middle surrounded by the 2 H's on the sides. Well, here's what water can do. To a very, 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 very small degree, water will dissociate. Just like if you put salt in water, the salt dissociates or breaks down into the sodium ions and the chloride ions. Water can do the same thing, but does it to a very small degree. Only a very slight number of molecules does it. Salt, all of the molecules do it until you get saturated. In water, a very, very, very small amount of water will dissociate into hydrogen ions and hydroxide ions. Now, if we're talking about pure water, for every water molecule that breaks apart, we get one H and we get one OH, and effectively the H component, that is the acid component, and the OH, that is the base component. And so since we have an acid component and a base component, the water itself is going to be neutral. It's going to have a pH of 7. If we can increase the number of H's, that will have a corresponding decrease to the number of OH's, and the solution would shift from neutral into the acidic range. And if we did the reverse of that, if we decreased the number of H's, the OH concentration would correspondingly increase, and that would shift the pH into the basic range of the spectrum. And so the pH depends on the concentrations of these two particles and their relationship to each other. And they do have this inverse relationship where if the H concentration increases, the OH concentration is going to decrease due to the nature of the solution and what happens in the solution. And so that is just this basic, you need to understand that relationship between the H and the OH. And so that is where the pH equation comes into play. The pH equation comes into play where it measures the concentration of the hydrogen ions in the solution. If the hydrogen ion concentration is equal to the hydroxide ion concentration, then we're going to be neutral and we'll be at a pH of 7. If, however, we start to add H's or add OH's or take away H's or take away OH's from the solution, then everything gets thrown out of whack and our pH shifts. And we measure the concentration of the hydrogen ions and we can get a new pH value for the equation. So let's look at the simple use of the pH equation for a couple of example questions. Okay, so here's an example. What is the pH of a solution that has a hydrogen ion concentration of 4.52 times 10 to the negative 8? Now, I think I'm pretty sure I've mentioned this, but just to make sure, whenever you see some chemical inside of brackets in chemistry, whatever chemical X may be, in this case it's the hydrogen ions, then what those brackets mean concentration. I'm out of room there. It means concentration. Now we measure concentration in molarity, and I probably should have put molarity here, but that's okay. So what is the pH of this solution? Well, we're going to use the pH equation. The pH is equal to the negative log of the hydrogen ion concentration. So all you're going to do is you're going to take your concentration that you have here and you're going to put it in to that spot right there, and you're going to punch it into your calculator. So the pH equals the negative log of 4.52 times 10 to the negative 8. Throw it in your calculator. If you have a TI calculator, you can just actually punch it in this order. Just hit the negative key, hit the log key, then type in this number and close off the parentheses. When you do that, you will get 7.34 as your pH value. If you don't have a TI calculator, you may have to punch the number in first, then hit the log, then take the negative. If you have questions about how to do that, just come see me. So if our pH is negative 7.4, sorry, not negative, but 7.34, a question I might ask you is this an acid solution, a neutral solution, or a basic solution? And so you ought to be able to figure that out pretty quickly and pretty easily once you know the pH. pHs that are greater than 7 are going to be basic solutions. And so this would be a basic solution to work with. And so that's how you do a simple pH problem. We also have what's called the pOH scale. Let me just show that one to you as well. It's the same formula. The pOH formula is the negative log. Instead of being the log of the H, we're going to look at the log of the OH concentration. And so you might see that equation in class as well, the pH equation, the pOH equation. And effectively the pH scale and the pOH scale are reverses of each other. And so if you look at the pH and the pOH scale next to each other, then you can see that they're just the inverse of each other. So the pH, the acids are 0 to 7. On the pOH, the acids are 14 to 7. And then vice versa on the other side. because as the pH goes up, the pOH goes down. So that's why we have this inverse relationship between the two. One thing to, and 7 is still neutral on both of them. One thing to note here, that's an interesting thing of note, if you take the pH of any, if you take the pH at any point on the scale, and you add it to the pOH at any point in the scale, then what do you get? So for example, let's just take this. What's the pH plus the pOH right here? 2 plus 12 equals 14. What's the pH plus the pOH right here? 9 plus 5 equals 14. The pH plus the pOH here is equal to 14. So we actually can create a new equation here. The pH plus the pOH is equal to 14. So if you ever have the pH and want to know the pOH, you just subtract it from 14, you get the pOH, or vice versa. And so that's just a nice little equation that is sometimes handy and useful if you want to do a conversion from pH to pOH. They will always equal to 14 when you add them together. And so at this point then you have three equations. I've given you the pH equation is the negative log of the hydrogen ion concentration. The pOH equation is the negative log of the OH concentration, and then we have the pH plus the pOH equals 14. So those are three equations that we'll probably be using in class some. That's it for today.